All right. Today we're going to introduce our final circuit component, which is called an inductor. So to motivate this, we're going to talk about what we did with capacitors, where we said capacitors are devices that are really good at trapping electric fields, and as such, they're really good at storing energy in an electric field. So today we're going to look at the magnetic analog of capacitors, which are inductors. And capacitors are usually two parallel plates, whereas inductors are just going to be a bunch of tightly wound coils, also known as a solenoid. So this is the base case of the inductor. There's obviously other things you can make. A coaxial cable is another one that sort of confines magnetic fields, but picture a coil when you look at inductors. So a defining feature of inductors is that since these are a bunch of tightly wound coils generating a magnetic field, any attempt to change the flux through these coils is going to result in an EMF because of Faraday's law. So these inductors are excellent at opposing changes in current. So inductors don't fight current, but they fight changes. And that sounds a lot like Lenz's law, right? Where we said if you're trying to change the flux through something, there's always going to be a back EMF that fights it. So inductors are really good in the long time case. When there's no changing current, inductors are happy. But as soon as you try to change the current through the inductor, they're going to get quite angry and induce an EMF to fight the change. And it can actually cancel out any effect initially. So this ability to resist the change in current is called inductance. And this is my least favorite symbol of the class. It's L. So that's what forced me to use cursive L for most of the year when making all of my lengths. This L stands for inductance because, of course, inductance is measured in units of henries. And like capacitors, inductance is usually not on the order of henries, but micro or milli. To represent inductors, we represent them as a solenoid or a bunch of curled loops. And this is our standard symbol. So to think about this formula, we know that this device, this inductor, is something that fights changes in current. And that is a manifestation of Faraday's law and Lenz's law. So we're going to define an inductor as a circuit component with this property, where it's going to induce an EMF to fight, that's why there's a negative sign, changing currents. So again, we'll say it again. Inductors do not fight current, inductors fight changing currents. So think of inductors as people who are stuck in their ways and they don't like change. But once you've given them enough time to warm up to an idea, they're going to be fine with it. So I always think about inductors as wherever you're trying to change something through them, they're literally going to wag their finger at you and say, "Oh, no, you don't." And they're going to fight it. So we'll give a pretty telling example here. A solenoid with inductance L experiences a increasing rightward current given by this expression. So it's an initial current to the right, and then it starts ramping up. So again, that's going to look something like this. So we know our current is increasing. And it is given that these are positive constants. So absolutely, the inductor is not happy with this. The inductor does not like that the current through it is increasing. So the inductor is going to try its best to say, "Oh, no, you don't. You're not increasing the current through me." And it's going to fight the change. So what does that mean? Well, the current at different times through this inductor is going to look something like this. So at one time, maybe it's a small rightward current, and a later time, it's a big rightward current. So the inductor is very displeased with this. So what the inductor does is the inductor fights the change. So it fights the change by turning into a battery. So we have to think, what type of battery is going to fight this? Well, this type of battery would generate a rightwards current. So the inductor absolutely doesn't want to do that. The inductor doesn't want to help the increase. The inductor fights it. So the inductor is going to turn into a battery like this. So what that means is that this inductor, this end will be positive relative to the right end. So it's not actually going to achieve its goals in completely canceling the change in current, but it will at least fight the change for a little bit. So indicate the induced polarity, we did that. So we can say that the left end is at a higher potential than the right end. So whenever we're talking about justifications with inductors, we'll use their property. They fight changes in current. So the inductor opposes the increasing rightward current. So that's how we get the polarity. You have to figure out what kind of mini battery will the inductor be. So if it was a decreasing rightward current, the battery would face the other way, because the inductor wouldn't want to see the current through it decrease, so it would have the right end be at a higher potential to support that. So just like with Lenz's law, we're trying to maintain that flux through the coils as what it currently is. All right, this is pretty easy. Derive an expression for the magnitude of the potential difference. So by definition, the inductor induces an EMF with magnitude L di dt. Because L is that just proportionality constant that determines how good it is at opposing. And of course, it should depend only on this current change. So our current function was defined to be I0 plus BT squared. So we just take a derivative and we get L times 2BT. So that's our induced EMF. Let's write it like this. 2 BLTs worth of EMFs. So pretty straightforward to plug in for that. So we can see the EMF through across the inductor, it starts opposing more and more and more and more, because you're not just ramping the current up slowly, it's actually increasing at an increasing rate. So the inductor is becoming more and more and more angry as you change that current. So now we got a huge little ranking task to do. Consider each of the following identical inductances. So we have some receiving constant current, some receiving growing current, some receiving decreasing current. And we're interested in this huge ranking of average EMF through each. So, of course, if we're ranking something, we need to get some sort of equation. And our ranking relies on the fact that we know the induced EMF in an inductor is L times the rate of change of current. So we are really just ranking rate of current change. And since we just want the average, and I actually give us that it's linear, we're just using delta I over delta t. There's no calculus required here. We can just take sort of a normal rate of change or a normal slope here. So let's do that. So we got a whole bunch of inductors to do. We got A, B, C, D, E, and F. So we can do each of those things. Inductor A, constant current. I can stop right here at constant current. Inductors don't care about current. Inductors care about changing current. So delta I equals 0. So this means EMF is 0. What about B? Has a larger current than A, but who cares? It's constant. Same idea. No current change, no EMF. Now we get to the actual computing. Inductor C, the current grows from 0 to 2 amps in 30 seconds. So the current changes by 2 amps in 30 seconds, which I'll simplify to 1/15 amps per second. What about D? D does an increase of 0 to 4 in 60. So it increases by 4 amps in 60 seconds, which is still 1/15 amps per second. And then E decreases from 2 to 0 in 15 seconds. Doesn't matter if it's an increase or decrease. So you actually change at 2/15 of an amp per second. And then inductor F shrinks from 4 to 0 in 60. So it's 4 over 60. So again, the rate of current change tells you how unhappy your inductor is, and we're given that L is the same for everybody, this proportionality constant. So we can just rank. So A and B, there's no induced EMF because it's constant current. So if you have constant current, your inductors are just like Mike Tomlin and they do not care. Then we have a three-way tie at C, D, and F. And then we have E. Because again, we really just ranked the current change. So here we had no delta I. Here we had our current change, our delta I over delta T was equal to 1/15 of an amp per second. And then same thing for E, except we had a larger change. So again, inductors are unhappy and are inducing EMFs to fight current change. So pretty straightforward ranking. Did there really need to be 6? Maybe not. But alas, here we are. We said inductors store energy just like capacitors do. So there's got to be a formula. And this is a nice looking formula. It looks very similar to some other energy formulas. More specifically, the energy stored in the magnetic field in the B field is 1/2 times Li squared. So L is the inductance, I is the current through it. So it actually helps to think about inductors or inductance as inertia. So inductance is this electrical inertia opposing change. If I apply a force on a refrigerator, it's not just going to instantly accelerate and start speeding up at a really, really quick rate. As I push on it, it's going to speed up slowly because that fridge has inertia. So yes, it'll accelerate, but is it going to reach its top speed instantly? No. So this L determines that sort of opposition to change. And current, if we say that this kind of matches with kinetic energy, we say that L is sort of the mass or your inertia. The I is your V, which makes sense because V is your speed that you're going. So current is also a rate of change, and it's sort of this flow. So I actually really like this analogy of inductors and inductance as like a mechanical analogy with mass and inertia. And you can go further than that and say magnetic flux is Li, which is momentum, and it goes pretty deep. It's a good analogy. And they've made it physical using this toy called Spintronics, where you can actually visualize this idea as they're sort of these spinning wheels that don't just stop instantly. Let's prove this. So, if we just hook up an inductor with current through it to a resistor, that current can't just go forever. There's no battery supplying current, so the current is going to eventually shrink to zero through this circuit. So that means if we can find the total energy that the resistor burns, we have found all the energy that was stored in the inductor's magnetic field. So let's do that. So first, we know that what we're interested in is total energy dissipated. So the total energy dissipated by the resistor is just all of the power dissipations times time, because power is the rate that you dissipate energy. And now for a resistor, we'll start with our definition of power, I delta V. Now, we can't just multiply, because we said that these inductors are going to oppose some change. So if this current is decreasing, well, it's not going to be a constant current. So we can't. And we're actually not in the section where we're deriving the formula yet, so it's probably not that involved. So now we can use a quick observation. Notice that the inductor and the resistor form a closed loop with each other. So what this means is that we can say that our delta V across the inductor is going to be equal and opposite to the delta V across the inductor, which is negative L di dt. Because again, EMF and potential difference, those are the same units. We usually use them interchangeably, EMF and voltage. So why can we say that? Well, just look at the loop rule. So let's say the inductor is acting as a battery. So if I gain some volts going across the inductor, I must drop exactly that by the time I go through the resistor. Or you can use the parallel rule, right? If this is parallel because they're connected to each other and nothing else. I know it looks like a series, but again, remember the definition of parallel is that you go through each other and back with nothing else. So that allows us to make the substitution that the resistor voltage and the inductor voltage are the same. Or at least one is the opposite of the other because they need to cancel by Kirchhoff loop rule. So let's do that. So we can plug in for delta V of the resistor now. So this means our total energy is just the integral of I, which is I, and delta V is negative L di dt dt. So we see something interesting happen, and this is actually really beneficial for us because it makes it so we don't need time dependence at all. So we see there's a dt in the numerator and a dt in the denominator. And that cancels. And also L is a constant, so let's pull out the negative L. So we get negative L times the integral of I times di. And now we can see where the formula is going to come from. So what are our integration limits? Well, it says the inductor supplies an initial current I0. So we know our current starts from I0. And we keep going until all of the current is gone. So we end with no current. So what does that do? Well, now we can just take our antiderivative, which is I squared over 2, right? Derivative of what is I, well, it's just I squared over 2. And we plug in from 0, from I0 to 0. So if we do that, we get negative, we'll pull out the 2, negative L over 2 times 0 squared minus I0 squared. And what do you know? The negatives cancel out, and we get 1/2 Li squared. Exactly as we expected to find for our energy dissipated. So just to zoom in on what we did, or zoom out, I guess, we said power. If you integrate all of the power, you get the total energy. For a resistor, the definition of that is I delta V. And we actually know what delta V is. We know what delta V is because it's connected to an inductor. So they must have the same delta V. So we plugged in. We had a nice relationship happen with our differentials to get rid of the time dependence. And then it just became a pretty easy antiderivative. So the total energy supplied by the inductor must be equal to the total energy dissipated by the resistor. So we say they're equal. So to calculate inductance, of course, we know it's this proportionality constant, but let's actually figure out what it depends on. So it might help to make a connection with our electrical analog of capacitance, which we defined as Q divided by delta V. It's how efficient your conductors were at storing charge per unit of potential difference. So, similarly, we can define this inductance as how efficient your coils are at confining magnetic flux per unit current. So we said that because delta V depended on the E field, which depended on the charge, we only got geometric factors affecting capacitance. So you could have things like the plate area, or the plate separation, or even the permittivity, but you couldn't get sigma or Q or rho. Like it had to be some sort of geometry factors. And we'll see this follows the same rules. Because if inductance tells you how good you are at storing flux per current, well, it depends on flux. And what is flux? Well, it's B field times area. And what affects B field? What generates B field? Moving charges, which are currents. So I will cancel out. So first, let's verify that this is the correct expression for L, consistent with our definition. So we said the induced EMF through a coil is negative to fight the change, depends on the rate of change of current, and L is a proportionality constant. But that's not the first time we encountered induced EMF. We said induced EMF, well, that's just Faraday's law. So we know that induced EMF depends on flux change. And if you have N coils, there's N contributions to that flux change. And well, now look, we have two different expressions for this same quantity. So they must be equal. So we can write negative L di dt is equal to negative N d flux dt. Notice everybody brought a dt and everybody brought a negative sign, so I can cancel and I can write L times di is equal to N times d flux. And now we can just add up all our contributions. So if we add up all of our current contributions, di, we get the total I. And if we add up all of our flux contributions, d phi, we get the total phi. So a lot of people actually just like this, kind of as the inductance formula, because it makes an analog to momentum. So we said that 1/2 Li squared is sort of your kinetic energy. Well, Li is your mass times velocity, or your momentum. So it makes sense that because Faraday's law says that a flux change is required to change the EMF or to induce an EMF. So This is similar to saying a force is needed to change your momentum. But of course, we wanted to solve for L. So L is defined as n phi divided by I. So also, this should like qualitatively make sense that this is a formula for inductance, because if your coil is really good at trapping flux for a certain current, it must be good at resisting changes. So this looks very similar to how we did capacitance, where we use one of our laws to derive an expression for a field, then we do some sort of integration over a field, and then we apply the expression. So in this case, we don't use Gauss, because Gauss is for E fields. We use Ampere. So Ampere's law gets us the B field, and then we find the total flux through the surface. In most cases, we're actually going to have a uniform B field, so no integration is required. Because 90% of the time, we're just doing a solenoid, which, like the parallel plate capacitor, has a constant uniform field. So we just multiply BA. So let's remind ourselves how to do the solenoid. So this is a solenoid that has capital N coils of cross-sectional area A, and it has total length lowercase l. The solenoid is wrapped around a rod with a permeability mu core. So this is not mu zero. This is going to be the same effect that a dielectric has for capacitors, where if you insert a material that's better at confining magnetic fields than vacuum or air, you get a better inductor. So let's do it first. Ampere's law, derive an expression for the magnetic field inside the solenoid. So this is a standard proof. Might have been a while since you've done it. But again, for Ampere's law, we know that Ampere's law says the integral of B dot dl is equal to mu, I'm just going to write this as mu, times I enclosed. Because mu is not mu zero in this problem, so let's not use mu zero. It's technically mu core. I'm just going to write that at the end. Okay, so we have to figure out what kind of field do I want to draw, and what kind of loop marries nicely with that field. So if I wrap my fingers sort of popping into the page and then curling this way, I get a field inside that's going to be uniform and to the left. So I know that inside my solenoid, I sort of get a leftward field like this. And again, this is our assumption of an ideal solenoid. Just like when we do the capacitor, we assume the plates are large so that it confines the field between them. We also agree that an ideal solenoid traps the field this way. So again, this is like a slinky. You can think of the field going right through the slinky like that. So what field marries nicely, or what loop marries nicely with this? Well, we don't want anything inside because we enclose no current. We don't want anything purely outside because we assume B equals 0 outside the solenoid. So we actually want a loop that's sort of halfway in and halfway out. And I know nothing about this path, so let's call this length x and hope it cancels. So let's do our circulation. So our circulation along this path is a B field B for a distance x along the bottom of the rectangle. And then since the field is entirely horizontal, you get nothing on this end, you get nothing on this side, and then outside there's no field, so it's still 0. So we get Bx as our net circulation. It's really Bx plus 0 plus 0 plus 0. And then what is my I enclosed? So let's figure that out. So we know that it's going to be I times coils enclosed. It's not capital N, because capital N would be if I enclosed the entire solenoid. So we have to do some accounting to figure out how many coils it actually is. So we can find the coils enclosed by saying there are capital N coils over a full length little l. So that's my sort of current or coil density. So this is the coils per unit length, and then I just multiply it by the enclosed length. And we see that, as expected, my magic X that shouldn't have physical significance actually cancels. So I get the expected B field result of mu times the fraction n divided by L times I. And this is our known result of B from a solenoid. It's just always good to review. So that's step one, get B. Next step is get flux, which is BA. So we're saying that our field is uniform. So we have a uniform B field. And we essentially have this. If this is one of our coils, our B field looks like this. I can even do better. I can do much better at that. So what that does for us is that allows us to say that flux through one loop is equal to B perp times A, and that's entirely perpendicular. And A was just the area given to us in the problem. There's no pi r squared or anything. We just call it A. So we just multiply our B field, mu naught n over L times I times A. And we're not actually done because we want the total flux. This is just the flux through one of the loops. So for our total flux, we just have to attach on another factor of n. So we just get mu, that was a really bad mu n squared IA divided by L. Okay, and as expected, the total flux does depend on I, so it's going to cancel now. What is the inductance of a solenoid? Well, L is defined as the total flux divided by the current. Total flux is mu n squared IA divided by L. And I'm dividing that entire thing by the current I. And notice the only thing that does is that just removes I. So I get mu from the core n squared A divided by L. So we get some interesting things going on with this. This is also a formula sheet expression, by the way, for E&M. We see that the more coils you have, the more inductance you have. So that's usually the easiest way to increase inductance, is just keep wrapping more and more coils, because the more coils you get, the more B field you get. So it is this quadratic dependence. Makes sense that having a larger coil area works in your favor, because that's more area to pierce with the B field. And then L goes on the denominator, because if L is big, your slinky is stretched out, so it's going to confine it less tightly. So makes sense. There are other cases of inductance that maybe you might have to do sometime, but I doubt it. The solenoid is kind of the base case. So that's kind of everything with inductance before we throw these things in circuits.